So welcome to this video on the pigeonhole principle. The pigeonhole principle is a foundational counting technique. Like its kindred spirits, the addition principle and the product principle, the pigeonhole principle gives us a vocabulary to talk about patterns in counting problems. And we use the pigeonhole principle when dealing with a tipping point phenomenon. A tipping point is the moment when we suddenly have enough small, local changes to cause a big, global change. The familiar idiom, the straw that breaks the camel's back, is actually about a tipping point. If we add one too many things, then there is an inevitable consequence. So let's see why the pigeonhole principle is a mathematical version of the last straw. The pigeonhole principle is easy to state. If n plus 1 balls are placed in n boxes, then at least one box contains 2 or more balls. Rather than talking about placing balls in boxes, we can talk metaphorically about placing pigeons into pigeonholes. And fun fact, the pigeonhole name actually refers to pigeonholes in office furniture used to sort and store letters or keys or other items. In fact, Dirichlet's original formulation talked about putting balls into boxes. More precisely, he placed pearls into cabinet drawers. So we'll either talk about putting balls into boxes or putting pigeons into pigeonholes. They both mean the same thing. Here's a nice proof of the pigeonhole principle. Let's say that we've distributed n plus 1 balls into n boxes. Then the average number of balls per box is n plus 1 divided by n, which is a number that is greater than 1. Now each box contains an integral number of balls, so some box must contain 2 or more balls. As a side note, this same argument says that some box contains at most 1 ball. Sometimes that complementary argument can be useful too. We also have the generalized pigeonhole principle. An example of this generalized version is that if we place 9 pigeons into 4 pigeonholes, then some pigeonhole must contain at least 3 pigeons. The most even distribution of birds would place 2 in each box, leaving 1 more pigeon that has to go somewhere. And so here is the generalized formulation of the pigeonhole principle. If n is some number that's greater than r times m, and we place n balls into m boxes, then at least one box contains r plus 1 or more balls. The proof of the generalized principle is very similar to the simple case. The average number of balls per box is greater than r, so this means at least one box contains more than r balls. At this point, you might be underwhelmed by the pigeonhole principle. It seems rather obvious, and you're right. When phrased this way, it is pretty easy, and that's why we call it a principle. But here's the reality of it. In many applications of the pigeonhole principle, the true challenge is realizing that we are dealing with a tipping point phenomenon. That flash of insight can be a hard-earned and remarkable moment. Here is a good example of this phenomenon. We must show that after placing 5 points in the unit square, there is a pair that are close to one another. Their distance is at most square root of 2 divided by 2. Note that this problem doesn't mention pigeons or pigeonholes or even balls and boxes. There isn't any hint that this problem should be solved using the pigeonhole principle. But given that I know that I'm supposed to use the pigeonhole principle, let's try to outsmart the problem. The 5 points are probably my pigeons, and since I'm above the tipping point, I'm supposed to come up with 4 pigeonholes to put them in. So how can I split up the unit square into 4 parts so that the maximum distance within each part is square root of 2 over 2? Here's the answer. Split the unit square into 4 squares, each with side length 1/2. The pigeonhole principle tells me that one of these squares must contain 2 of my 5 points, and the maximum distance in that smaller square is square root of 2 over 2. So I'm guaranteed that there are 2 points that are within my required distance. And I do want to point out one thing. This proof is valid, but it does not necessarily find the closest pair of points. In this case, those closest points are actually in 2 different boxes. But that's okay. We weren't asked to find the closest pair of points. We were asked to find a pair of points that are close enough. Here's another example that is a little more straightforward. Let's consider a function from a set of size n squared plus 1 to a set of size n. What can I conclude about this function by using the generalized pigeonhole principle? I want you to pause the video and come up with an answer. The first thing you need to do is to decide what your pigeons are and what your pigeonholes are. And here's a hint. You need to have more pigeons than pigeonholes. So give it a try. Okay, we need to have more pigeons than pigeonholes, so let's take our domain to be the pigeons and our target set to be the pigeonholes. So I am mapping n squared plus 1 elements to n elements. Therefore, my average pre-image size is n squared plus 1 divided by n, which is larger than n. So I can conclude that some element in the target set is being mapped to at least n plus 1 times. Let's summarize what we've seen. Pigeonhole principles are about tipping points, and the hardest part of a pigeonhole problem is determining what the pigeons and the pigeonholes are. Sometimes concocting these pigeonholes requires a serious aha moment. And here's the you try problem for this video. It requires one of those aha moments. We start with a set containing 2n elements, and someone hands you a subset S of n plus 1 elements. You must convince me that S contains 2 elements that sum to 2n plus 1. And now keep in mind, you do not get to pick the set S. Your argument has to work for every possible set of size n plus 1. Good luck. Have fun.